Hi, I'm Zor. Welcome to Unizor Education. Today we will consider another type of a function. It's called exponential function. And let me start from the definition, and then I will go into the explanation of what it actually means. So the definition of the exponential function is this. So x is an argument, y is the value of the function, and a is any real number. Well, actually 0 is not an interesting one. Let's forget about the 0. So a is positive. Now x is all real numbers. Well, it's fine to define something, but then I have to explain what I really mean, right? All right. Let me start from a very simple case. If x is natural number, usually when we are talking about natural numbers, we try to use some letters like m, n, or k, or whatever. So let's talk about a to the power of n, where n is natural number. Actually, we do know what that means. By definition, this is a times a, etc., times a, n times. Now, that's easy. Okay, so the definition of the exponential function for natural exponent, this is called exponent. A is a base, x is exponent. So for natural number as an exponent, it's very easy to define. That's exactly how we did it. What if I want something like 2 to the power of 1/3? That's not as intuitively, at least looking at this particular definition, right? So we have to really explain what we mean. And that's exactly what this particular introduction into the exponential function is about. So this lecture is about what exactly we mean when the exponent is basically any real number. And I will gradually build this particular explanation step by step, basically increasing the complexity of that thing. So as a result, you will know what a to the power of x means for any real number x. Okay, let's start from the beginning now, and let's expand our obvious definition of exponential function for natural exponents. Let's expand it towards more and more different numbers. Now, before doing that, I would like actually to point two very important properties of this particular expression where a is a positive real number and n is natural number. So I would like to mention a couple of very important properties, because I would like these properties to be preserved for all other types of exponent, rational, irrational, negative, zero, etc., etc. Because if we want to reasonably define the exponent for non-natural numbers, like rational, for instance, we would like certain properties, good properties, which we can observe with natural exponent. We would like these properties to be preserved for all other types of arguments, types of exponents. So what are these important properties which I would like to preserve for all other types of exponent? Here is the most important one. If I have a sum of two different natural numbers as an exponent, this is, let's just think about what it is. This is a to the m plus n power, which means it's a times a, etc., times a m plus n times, right? Now, if this is m plus n times, where n, m, and n are natural numbers, then I have m times and n times, correct? Now, this piece is a to the mth power. And this is a to the nth power. And they are multiplied by each other. So this is a very important property of natural exponents. Just as an example, 2 to the power of, let's say, 6 is what? 64, right? Now, 2 to the power of 4 is 16, and 2 to the power of 2 is 4. 2 to the power of 6 is equal to 2 power of 4 times 2 power of 2, because 6 is 4 plus 2. 16 times 4 is 64. What did I put here? I'm sorry. I mean that. Right? So 16 times 4 is 64. So this is obviously preserved. I mean, this is not a proof. Proof I did before. This is just an illustration that this is a very important property of exponents. Now, if I am a reasonable person and I'm trying to expand the definition of the exponent to other non-natural numbers, I would like to define it in some way where this particular property is preserved. I mean, otherwise it looks like for some numbers the property does exist and for some other it does not exist. I would not consider it reasonable. I mean, probably I could do some crazy definition like that, but why? I really should try to define the function a to the power of anything in such a way that this important property is preserved. By the way, this important property can be just slightly expanded towards more than one numbers added together. So if you have m1 plus m2 plus m3 plus etc. plus mk, then it's obviously can be written as a to the power of 1 times a to the power m2, etc., a to the power mk. The proof can be, I mean, rigorous proof can be done by induction. Non-rigorous proof is just obvious because this is a times a times a this number of times, and we just divide this product of m plus m1 plus m2 plus etc. Times a. We divide it into groups m1, m2, mk times product of a by itself. So this is obvious, and one of the consequences from this is if all m1, m2, m3, etc. are equal to each other, and they are equal to some number m, so I will have a to the power of m plus m plus m plus m k times, right? So it's k times m. And this is what? It's a times to the mth power 1, 2, 3 k times, which is this. So this is yet another property which is obviously a consequence of this one. And it's all based on the same property that the addition of exponents results in the product of the exponential functions. All right, let's just remember this and this. So let me just put it on the top. So we will have a reference to these two things. A to the power m times k is equal a to the m to the power of k. Oh, incidentally, it's also equal to a to the power of k to the power of m, because m and k are commuting to each other. All right, so these are properties, and we would like to preserve them for all other types of exponents, not necessarily the natural. Now, the first is 0. What is m is equal to 0? Well, in theory, I can have some philosophical discussion about if a to the power of m is a multiplied by itself m times, then a to the power of 0 means a multiplied by itself 0 times. But what is this 0 times multiplication? I don't know what it is. But let's go into this rule and let's try to basically use this rule to find out what is a reasonable value for a to the power of 0, and then just define that a to the power of 0 is this reasonable value. That's how people do. So our definition must be based on some logic, and here is the logic. A to the power of n is equal to a to the power n plus 0, right? Because n is equal to n plus 0. Now, using this rule, n plus 0, I will just use it formally. It's a to the power of n times a to the power of 0. We would like this rule to be preserved, and what follows from here, a to the n's, this is a to the n's times something. Now, what is this something can be? Only 1, because only multiplication by 1 leaves a to the power of n without any change. So from this equation, if you wish, we derive that a to the power of 0, which we don't really know what it is because it's not defined, but it must be equal to 1 just to be a reasonable definition. Because if this definition is not like this, if it's something else, if it's some other number than 1, then if we add 0 to our repertoire of different exponents, we will not have this property preserved. So we must define a to the power of 0 as equal to 1 unconditionally, regardless of the value of the base a, by the way. So no matter what the base is, if you use a to the power of 0, it must be equal to 1, otherwise this will not be preserved. So that's the definition. We came up with a definition. It's not a proof. Let me just point it again. It's not a proof that a to the power of 0 is 1. It's a logic which is behind the definition. So a to the power of 0 is equal to 1 by definition, but the logic behind it is this one, because we don't want to break this particular property. Okay, fine. So we have defined a to the power of 0 is always 1 regardless of the base a. Next, let's expand to negative numbers, negative integer numbers. A to the power of, I'll put it minus n, assuming that n is natural number, 1, 2, 3, etc. So it will be a to the power of minus 1, or minus 2, or minus 300, etc. So how this can be defined? Well, let's do this little operation. A to the power of n times a to the power of minus n. According to this, it's this. Right? If you multiply these, you add the exponents. Now, this is obviously a to the power of 0. N plus minus n, right? And we already know this is 1. Now, what follows from this is the following. That a to the power of minus n, this one, must be equal to 1 over a to the power of n. Let's disregard the phone. Okay, so basically this is something which is, again, a definition, but it's a reasonable definition, primarily because we want this property to be preserved. If we don't do this, if we don't define it as such, then I probably would not have this particular equality, so this property would not be preserved. To preserve the property, I have to define a to the power of minus n as 1 over a to the power of n. Again, this is a definition, but it's a reasonable definition because the property is preserved. So, we have defined a to some power in many different cases right now. We defined it for natural numbers as the multiplication of a by itself. a certain number of times. We defined it for 0, which is always unconditionally equal to 1, regardless of the base a. And we have defined it for negative integers. So a to the power of minus 2, let's say, this is 1 over a to the power of 2. By the way, here I explicitly use that a is not equal to 0. Now, the fact that it's positive is not maybe used so far, but it will be used in the future, because I would like to expand to, let's say, square roots of something, and we don't really know how to, I mean, we do know that square roots of some real numbers can be expanded into complex numbers, but we're not talking about complex right now, only real numbers. So we are dealing with real numbers, and that's why a should be always positive. Okay, so we've done that. And let's now go into a little bit more complex case. Okay, so what after positive and negative and 0 integer numbers? Well, we have to expand it to rational numbers, all right? So let's just think about rational numbers and what is a reasonable definition for exponent being a rational number. Okay. Let me start with the following. What is a? I can always put a as a to the first degree, first power of 1, right? Because it's a times itself 1 time, which is a. Now, 1 can always be presented as q divided by q, where q is integer positive number, natural number, right? So q is natural number. So q over q is always 1. Now, what is q over q? I can always present it as a over, in the power of 1 over q plus 1 over q plus etc. plus 1 over q, where I add 1 over q times, right? It is the same thing, like 3/3 is 1/3 plus 1/3 plus 1/3. So q's is 1 q's plus 1 q's plus 1 q's, etc., q times. Now, I will use this property that adding exponents results in the product of exponential functions. So it's a it's a to the power of 1 over q times a to the power of 1 over q times etc. times a to the power 1q, not plus, it's multiplication. 1, 2, 3, 4, q times, right? This is q times we add 1 q's to itself, so this is q times multiplying a to the power of 1 q's by itself, which is equal to a to the power of 1 over q to the power of q. Now, let's recall that if you have b to the power of, let's say, m equals to a, what does it mean? It means that b is equal to mth root of a, right? This is definition. What is mth root of a? It's such a number b which being raised into the mth power results in b, right? That's the definition. So basically, what I can say in this particular case, a to the 1 over q power 1 over q is basically my b in this case. So a to the power of 1 over q is equal to q's root of a. So we all know what q's root of a is. it's defined as the number being raised into the power of q gives a. So that's what a to the power of 1 q's is by definition. Again, this is a definition, it's not a proof. The definition of a to the power of 1 q's, where q is natural number, is q's root of a. It's a reasonable definition because we have this basically, the same property is preserved. So that's it. And the only thing which we have, well, not the only thing, just a little bit more. We have to define a to the power of p over q, where p and q are natural numbers, positive integer numbers. What is this? Well, you can always consider this as a to the power of 1q to the power of p, right? Using this property. This is p over q is p times 1q's. So it's a to the power of 1q's in the power of raised to the power of p. Now, we know what this is. So it's q's root of a. So that's to the p degree. And from this, we very easily deduce that this is equal to the a to the power of p as the first, then being rooted, I don't know, by q's degree, which is the same thing basically as you can do it conversely. This is a to the power of p to the power of 1q's. This is exactly the same thing. The q's root of a to the power of p. So no matter how we use, as I said, these are symmetrical things. So no matter how we do it, we derive with the same conclusion, that a to the power of p over q, where p and q are natural numbers, is the q's root of a to the power of p. Okay, it's almost done with rational numbers, because all we have to do is to add negative numbers. But we already know how negativity actually affects. So if this is a negative number, negative rational number, let's say it's a to the power of minus p over q, where p and q are natural. So this is a negative natural number, right? Now, we all know what negativity actually does. If you remember, a to the power of minus m is equal to 1 over a to the power of m. We would like to preserve it, right? So to preserve it, all we have to do is define negative rational power exponent as 1 over q's root of a to the power of p. That's it. It's a definition which I have derived from everything which I've had before. Power of p over q. I mean, I can do it in 2 steps actually. This is minus 1 times p over q, which is a to the power of p over q minus 1. Minus 1 gives me 1 over, and the a to the power of p over q gives me q's root of a to the power of q. So no matter how we do it, this is a definition for negative rational numbers. What's left is only the irrational numbers. And here is where robustness and rigidity, rigorousness of all this theory actually breaks, I would say, a little bit. You see, to properly define real numbers, we need the theory of limits, which is addressed in these lectures, but a little later. So that's why I'm using semi-rigorous description of real numbers as being approximated, however precisely, by rational numbers. So I can always say that if rational number p over q is an approximation for the real number r, then a to the power of p over q is approximation of a to the power of real number r. The more precisely we define this, the more precisely this is actually defined. So the property, since this property is preserved for rational exponents, using this approximation behind which is actually the theory of limits stands. But anyway, without mentioning the theory of limits, let's just think about approximation. Since the approximate value observes this particular quality, this character, it has this particular characteristic, then the any irrational, any real number, therefore, has the same property, and it's defined this particular way. So I might or might not actually address this more rigorously with real numbers. Quite frankly, I don't see the need for this. But for instance, if you want to know what is, let's say, 2 to the power of square root of 2, which is irrational number, all I can suggest you is use 2 to the power of 1.4 as an approximation, or 2 to the power of 1.41 as an approximation, etc. So I'm using these decimals, but at the same time I obviously can use 14/10 or 1/41, which is the same thing, and it adheres to our definition of rational exponent. So these are approximations. And obviously I can say that if this, let me just clear it out. If I want to know, for instance, what is 10 to the square root of 2 plus square root of 3 exponent, I can always say that this is 10 to the power of square root of 2 times 10 to the power of square root of 3, which in turn approximately equal to 10 to the power of 1/41 times 10 to the power of, I don't remember exactly, it's something like 1.7, so it's 72 or something like this hundredths. So no matter what it is, it's more or less approximating. Let's stop here, let's not go any deeper, which I don't really think there is a need. What is actually important is to notice that this property, if you add two exponents, even irrational exponents, it still can be broken into the product of two components, it's still preserved. So the definition using the approximation with rational exponents really works for irrational as well. So you have the right to have this particular equality even if 10 to the power of irrational number is not very rigorously defined, but you can definitely consider it as the one which we have basically defined. But now let's think about this differently. This is equal to 10. What is square root of 2? We already know that this is 2 to the power of 1/2, right? Because this is the square root. 2 is the root of 2, right? And this is 10 to the power of 2 to the power of 3 to the power of 2. Now, what's very important in this case are these parentheses, because obviously this is not the same as this. You see, I put parentheses differently here, and it's a completely different number, because 10 to the power of 2 is 100. 100 to the power of 1/2 is the root of the second degree of 100, which is 10. So this is 10. Now, this, or this, is definitely not 10. 10 to the power of square root of 2 is 10 to the power of 1.4 something, which is greater than 10, obviously. So these parentheses are very important, and you have to really be very careful when you are presented with the problem and the parentheses are at certain place. You do not really freely change these parentheses. It's not like you have associativity law. If you remember, if you have the same kind of operations like 2 times 3 times 5, you can put parentheses here, or you can put parentheses here, and they are equal to each other. This is commutative law. This is not a commutative law. So the power is not a commutative operation. Because if you put parentheses here, 3 to the 5th degree, I can't even count how much it is, but it's definitely not equal to 2 to the 3rd degree to the 5th degree. That's not the case. Now, why? Let's just think about why. Product is symmetrical operation. AB, BA, it's exactly the same thing. Raising to a power is not symmetrical because one is a base and another is an exponent, which do have a relationship, but they're not symmetrical relationship. 2 to the 3rd degree is 8. 3 to the 2nd degree is 9. They're not equal to each other. So the operation of raising into power is not commutative and definitely not associative. So it's a completely different animals. You cannot really deal with them the same way as with products or summation operation. Nevertheless, the purpose of this lecture was to define the operation of raising into some power, raising a positive number, base to some power, to define this raising into power for different exponents being, they may be either natural numbers, they can be 0, can be negative integer numbers, can be a rational number or negative rational number, positive or negative, or it can be irrational number, which means we cover completely all the sets, all the set of real numbers. So that's why we can talk about this function where a is greater than 0 and x is any real number as a function which has a domain of all real numbers. Now, the properties of this function will be discussed in the next lecture. So for today, I wanted just do the introduction. Notes are on this side, as always. Try to review them again. The purpose was to define, and again, don't forget, this is a definition of a to the power of something. It's not the proof that a to the power of 0, let's say, equals to 1. It's a definition, but the logic was needed to basically demonstrate that the properties of thus defined exponents are the same as the properties when the exponent is natural number. So that's very important. That's it. Thank you very much for today, and don't forget that the next lecture in this topic will be dedicated to the properties of the function, which we can consider right now as fully defined for all real numbers x. Thank you very much. Hi, I'm Zor. Welcome to Unizor Education. I will continue talking about exponential functions. The previous lecture was dedicated to basically definitions of what is an exponent is. Well, obviously it's very easy to define for natural number as an exponent. So if you have where x is a natural number, then it's just multiplication of a by itself n times. But then I expanded this definition to rational number, zero, negative numbers, irrational numbers, basically all based on one very important property of exponent, that if you have a product of two elements, each one of them is some base and some exponent, then it's equal to this. So the product of exponents is exponent of a sum with the same base, obviously. Now, this is a fundamental property of exponential functions, and all definitions in the previous lecture were based on this. Now I will go into properties of exponential functions. Now, just to illustrate these properties, I would like you to have in mind a graph of this particular function. I will explain all the details about graph in the next lecture. This lecture is about properties, but the graph is based on the property, and that's why I would like you just to keep in mind how the general picture actually looks like. So, now, this function is defined for all positive a, and we have to define it in two different categories, a greater than 1 and a less than 1. So for a greater than 1, the graph looks like this. It's increasing from 0 to plus infinity. And in this particular case, it's decreasing. Okay, now I draw these graphs without basically any kind of a base, any foundation. The foundation is the properties which I'm going to talk about this lecture, and the graph will be more explained in more details in the next lecture. However, it's easy to talk about properties if you have these pictures in mind, because I have it in my mind. That's why I would like you to have it. For greater than 1 base, it's increasing. For less than 1, it's decreasing. Now, having this picture in mind, now I will go to all the properties. And again, these are the properties which are in the foundation of graphing the function. So that's why it's very important. Okay, property number 1. Exponential function is always positive. Now, I will try to prove as rigorously as possible all these properties. So just bear with me. Now, why a to the power of x is positive? Well, let's consider again the definition, starting from the x natural. So a to the power of n is a times a, etc. A is always a positive number, so if you multiply positive number by positive number, it will be positive number. So for any natural n, it's positive. Now, for negative integer, where n is natural, so it's minus n. This is, by definition, 1 over a to the power of n, inverse. Now, inverse to a positive number is still positive. Inverse to 3 is 1/3. Inverse to a million is 1 millionth, still positive number. So for all integers, positive and negative, the a to the power of x is positive. Now, how about rational numbers? Well, again, what is a to the power of p over q, where p and q are two natural numbers? Well, again, by definition, this is the q's root of a to the power of p. Now, a to the power of p is positive. Now, q's root also positive. Basically, it's a definition of the root. Root is always positive from the positive number. We are not talking about negative numbers, complex numbers, etc. We are talking about positive numbers, and root of the positive number is always the positive number, which, being raised into the q's power, will give a to the power of p. And obviously, with a negative rational numbers where p and q are natural. This is again by definition, and since this is positive, the inverse is also positive. Now, just once I will address the irrational numbers, and then I will not talk about the rational numbers at all, because I cannot really make it absolutely rigorously. So I was talking about exponential function with x being an irrational number as a limit case when we are approximating this irrational number with rational numbers. So if x can be approximated with a sequence of rational numbers, then a to the power x would be a limit of a to the power of all these elements of the sequence. So basically, I don't want to go any deeper in this because, again, we are not really on the level where I can make it absolutely rigorously. So just consider the irrational number as a limit case for rational numbers, and that would probably be enough to talk about, well, the proof that a to the power of x would be always positive regardless of x. Positive x, negative x, anything. How about 0? How about a to the power of 0? Well, this is always 1 by definition. Again, that's from the previous lecture. And that's basically is based, again, on the main property of the exponential function. We must have a to the power of 0 equals to 1 to satisfy this. And again, that was addressed in the previous lecture. So if exponent itself is equal to 0, then the exponential function is equal to always 1. Okay, how about base? What if base is equal to 0? What happens then? Well, then exponential function is always equal to 1, because 1 to any power would be equal to 1. Proof is exactly the same as I was talking about a to the power of x being positive. First, you check it for natural numbers, which is 1 times 1 times 1 times 1. So for all natural x is obvious, that's 1. Then negative natural numbers, which is 1 over 1, which is 1. And then rational, etc. It's very, very trivial, so we're not going to address it anymore. Next property. All right, next property is actually related to these two graphs which I draw before. So basically it says that if a is greater than 1, then for positive x, y would be greater than 1, and for negative x, y would be less than 1. Again, remember the graph? Well, this is 1. So this is y to the power of, let's say, 2 to the power of x, something like this. Any number base greater than 1. So it's increasing. This is level 1. So if x is equal to 0, function is equal to 1. 2 to the power of 0 as anything else to the power of 0 would be 1. Then function goes above 1 to the right and below 1 to the left. Now let's prove it. Forget about graph. Let's prove it. Okay. Proof is exactly done in the fashion as before. First, well, let's consider this case. So if x is natural, a to the power of n is a times a times a n times. Now each a is greater than 1, as we are saying. Now multiplying a greater than 1 number by greater than 1 number results in greater than 1 number. If it's not obvious, let me just prove it to you. Well, if a is greater than 1, then It's just an interesting exercise. A can be represented as 1 plus d, where d is greater than 0, right? So if a is greater than 1, then d is some number greater than 0. Basically, d is equal to a minus 1, right? Now, therefore, a squared is equal to 1 plus d squared, which is 1 plus 2d plus d squared. Now, d is greater than 1, so we add something to the 1, which means we are getting a number greater than 1. So multiplying a number greater than 1 by itself 2 times will result in a number even greater than 1. Well, basically this is the way how we can prove that any number of times we are multiplying a number by itself, we will get the number greater than 1. Well, the easiest way probably would be something like this. This is greater than 1 plus 2d, right? Because there is one extra member here. So, now let's go to a to the third degree. We will have 1 plus d to the third degree, which is equal to 1 plus d to the second degree times 1 plus d, which is greater than, I replace this with this. Which is equal to 1 plus 3d plus 2d squared, right? Which is greater than 1 plus 3d. So, look at this. A squared greater than 1 plus 2d, a cubed greater than 1 plus 3d. Now, it's very easy to prove, let's say by induction, that greater than 1 plus n times a. Basically, that's enough to prove that it's greater than 1. And the greater n is, the greater this number becomes. So let's just remember this particular inequality. I do encourage you to prove it by induction. Just check it for n is equal to 1, which is kind of, or n is equal to 2, starting from n equals to 2, which is obvious. And then if it's equal, if this inequality is true for some number n is equal to k, try to go to k plus 1. Do it yourself, it's very easy, and we will use it in some other place. But what it proves for us right now is that if a is greater than 1, then for all natural numbers, which are integer positive, a to the power of n would be greater than 1. We see it from here. How about negative natural numbers? What if we are talking about this? Well, since this is equal to this is greater, denominator is greater than 1, so the inverse to a number which is greater than 1 is smaller than 1. So we get this one. Alright, so we have proved it for all integer numbers. How about rational? Quite frankly, it's exactly the same thing. Let's again start with this. If you have a to the power of p over q, which is by definition a q's root of a to the power of p, now this we have already proven that in this case this is positive. This is greater than 1, sorry. Positive obviously as well. Now, if you have a q's root from a number which is greater than 1, you must have the result which is greater than 1. Why? Otherwise, if it's less than 1, and then you will raise it into the power of q, every time you multiply it by itself, it will be smaller and smaller and smaller, because you assume that the number is less than 1. So it cannot be greater than 1 in this particular case. So that's obvious too. Similarly, with negative rational numbers, since this is greater than 1, then negative should be correspondingly inverse to a number which is greater than 1, that is a smaller than 1 number. So I proved it for all rational numbers. And I told you I will not talk about irrational numbers, but let me just say it again, that irrational numbers are a limit case of rational, so whatever the rational numbers inequalities are true for irrational numbers will always be true. Okay, now, very similarly, what if a is less than 1? Well, then I'm saying that for positive x, y would be less than 1, and for negative x, it would be greater than 1. Well, I can prove it directly in exactly the same or similar fashion that I did it for a greater than 1, but let me do it slightly differently. Look at this. A to the power of x is equal to 1 over a to the power of minus x. That's obvious, right? Because what is minus x? Minus x means 1 over a to the power of x, right? Which is a to the power of x. Now, having done that, I can basically refer everything to an opposite case. Because if a is less than 1, then 1 over a is greater than 1, right? So this to the power of x would be greater than 1 for x positive, and would be less than 1 for x negative, right? So for a, it would be vice versa, since this is equal to, so since 1 over a to the power of x is greater than 1, then a to the power of x should be less than 1 for positive x. And if 1 over a over x is less than 1 for negative, then y over x should be greater than 1 for negative x. So that's basically kind of a easy logic which will reduce these cases to these cases. Just change the sign of the exponent. Okay, so back to our graph. Again, remember, for a greater than 1, it goes this way. For a less than 1, it goes this way. Now, it looks like it's monotonically increasing or monotonically decreasing. So let's prove it, right? Why do I have, such a nice and smooth curve? Let's prove the monotonicity. Is there such a word, monotonicity? I don't know, maybe. So let's prove that the functions are monotonic for any a. For a greater than 1, it's monotonically increasing. For a less than 1, it's monotonically decreasing. All right, so let's consider this case. Now, now what is monotonically increasing? It means if we are increasing an argument, then the function is also increasing. That's what monotonic increase means. All right, fine. So let's just take two different arguments, and we start with integer arguments, positive integer numbers. So let's say m less than n. So I will prove that if this is true, then a to the power of m would be less than a to the power of n. How can I prove that? Well, very easily. Since m is less than n, then m is equal to n minus n minus n. Right? Right. Or, if you wish, n is equal to m plus n minus n. Same thing. So I will use this, actually. Now, a to the power of n, this one, therefore is equal to the a power to the power of m plus m n minus m. equals. Now, you remember that whenever we are adding exponents, it means we can multiply exponential functions. Now, a is greater than 1, right? So, this, considering that n minus m is greater than 0, this is greater than 1, right? It's base which is greater than 1 to the positive exponent, positive power. The result is, based on whatever we were just talking before that, greater than 1. Since it's greater than 1, then this number, a to the power of n, excuse me, is greater than a to the power of m, since this multiplier is greater than 1. So, we have proven that with increasing exponent, we increase the exponential function value as well for greater than 1 base. So basically it's really looking like the curve goes up, but only for integer numbers. Now, how can we expand it to, let's say, rational numbers? Well, it's really very, very similar. Let's say we have two different rational numbers, p over q, which is less than r over s. I have to prove that a to the power of p over q is less than a to the power of r over s. Now, how can I prove that? Well, let me first bring these two rational numbers to common denominator. Doesn't change the numbers themselves, so let's say I will use common denominator qs. So one would be p s over qs less than r q over qs, right? So these are exactly the same. But now, oh, I'm sorry, qs. But now I have an advantage of having common denominator. So it's easier for me to consider the same kind of a theorem only for cases of common denominator, because if denominator is not the same, I'll just bring them to common denominator. So let me forget about this particular case, and I will use the case when denominator is the same. Let's say u over w less than v over w, and I would like to prove from this that a to the power of u over w is less than a to the power v over w. So now I'm using the same w as denominator. Now, how can I prove this? You see, this means that u is less than v, right? They're all positive. We have already agreed that these are rational numbers with natural nominators and numerators and denominators. So obviously, since the denominator is the same, my numerators must be of the same relationship. Therefore, since I have already proven it for integer positive numbers, for natural numbers, a to the power of u is less than a to the power of v for greater than 1 base a. Now, all I have to do now is extract the w's root from it, right? Because a to the power u over w is w's root from a to the power of u. And a to the power of v over w is, again, w's, the same w's root of a to the power of v. Now, if a to the power of u and a to the power of v are of this particular relation, then their w's roots also should be in exactly the same relation, because if it's otherwise, then by multiplying greater number, the same w number of times, I will get greater number. So that's why the roots are supposed to be also in the same relation as a to the power of u and a to the power of v. Cannot be otherwise. If it's otherwise, I will just raise both in w's power, and I will have a reverse equation here. So I've proved it for real, rational numbers as well. Fine. Now, these are all positive numbers. I was only talking about positive numbers and prove that. How can I prove it for negative numbers? Again, let's start from integers. Negative integer numbers. Let's say I have minus m. Well, let's first do this. This is minus m, and this is minus n. So minus m is less than minus n. Now m and n are positive numbers. That's why I put minus in front of them. M and n are natural numbers. And since this one is to the left, from this one, this is the relationship. I would like to prove that a to the power minus m is less than a to the power of minus m. Now, how can I prove that? Well, very easily. Now, if minus m less than minus n, then m, the positive, corresponding positive, which is basically distance from 0, is greater than n. Therefore, from the previous case, when both are integers, if this is greater than this, then a to the m is greater than a to the n. Now, what is this? This is 1 over a to the m. And what is this? It's 1 over a to the power of n. Now, if denominators are in this relationship, then the whole fractions are in the opposite relation, right? Because if denominator is greater with the same numerator, then the fraction is smaller, and vice versa. Okay, so basically that's what we have just proven. Which means that the same monotonic property exists for negative integers as well. Now, absolutely the same way you go to the negative rational numbers, and if you have a mixture of negative and positive argument, it's even easier because we know that for greater than 1 base, everything to the right of the 0 is greater than 1, and everything to the left of the 0 is smaller than 1, which means we still have exactly the same type of relationship between the values of the exponential function. Okay. Now, the case with a less than 1, I will not consider at all, because again, it's quite obvious from the fact that if a is less than 1, then 1 over a is greater than 1. So all the properties of this case are true for this case, just reversing the sign of the exponent. Whatever was true for positive exponent here will be true for negative here, and vice versa. So that's why I'm not going to waste any time on this. That's obvious. Next property. So monotonicity to be proved now. Okay, we have to prove that a to the power of x for a greater than 1 increases to plus infinity if x goes to plus infinity. Okay, let me say it again. I'm using some symbolics here. So for this function, well, function is already written here, so we don't have to write it here. If base is greater than 1, if base is greater than 1, therefore y goes up to plus infinity when x goes to plus infinity. So it's not only monotonically increasing, but it's increasing to infinity. How to prove it? Very easy. We actually did something very useful. You remember, I've proven this just before, a couple of minutes before. For a greater than 1, if you are raising it to the power of n, you will get the value greater than this one. Now, how can I prove that this thing goes to infinity with increasing exponent n? Well, very easy. Let's choose any number n. And now I'm going to find such a number, lowercase n, that this thing exceeds this one. How? Well, let me choose the number n that this thing exceeds n. Now, when will this will be greater than n? Well, obviously, if n would be greater than n minus 1 divided by a, right? Minus 1 divided by a. So, as long as I choose any integer number n greater than this number, then 1 plus na would be greater than n, and a to the nth power will be even greater. So it will exceed the number n. So for any number n, I can find lowercase n such that a to the power of lowercase n will exceed it. Which means that for any level, I eventually will find the point where a to the power of n will exceed it. So that is actually the meaning of the statement that a to the power of x goes to infinity. At least we have proved this thing for all integers. So I can find an integer where it goes above certain level. But now let's think about the rational numbers. Since I have already proved that the function is monotonically increasing, once I found one particular point, let's say it's an integer lowercase n, where we have exceeded this uppercase n, then everything above that would be even higher. So that's what actually is a proof that the function goes to plus infinity. It's monotonic and it can exceed any, however large, chosen number n. So what we have just proven is that for greater than 1 base, the function goes to plus infinity when the exponent increases to plus infinity. Now, how about the next my statement? Well, this is not a straight line, I'm sorry. Now, my next statement is that when I go to the minus infinity, when argument goes to negative infinity, then the function goes to 0. Well, this is actually quite obvious. Why? Because for negative number x, I have this particular equation, right? This is the definition of negative exponent. So if a to the nth power, n is a natural number. So if a to the nth power goes to plus infinity, then 1 over a to the nth power goes to 0, right? 1 divided by a large denominator gives you a smaller fraction. And as soon as we understand that in this particular fraction, the denominator goes to positive infinity, we saw that the whole fraction goes to positive 0. Okay, fine. So I've got it for negative rational numbers, for negative integer numbers. So for negative rational numbers, it's obviously following from the fact that the function is monotonic. Okay. Next. Okay. So we were actually comparing the values of the function based on different values of the exponent x. Now I would like to compare how the functions look if we are changing the base. Base is not really an argument, but it would be interesting to find out how this function is different from this function. So my statement is that the bigger this particular base of exponential function, let's talk about this case. So the bigger the base, the steeper the function goes up. This is 2 to the power of x. And this is 3 to the power of x. So, the bigger the base, the steeper it goes up to the right, and faster it goes to 0 to the left. Now, with opposite a less than 1, we will have a similar kind of a relationship, but we will talk about this later. So right now, let me prove the following. That for a and b greater than 1, if a greater than b, then so if a greater than b, then a to the power of x is greater than b to the power of x for x positive, and a to the power of x is less than b to the power of x if x is negative. Right? So if this base is greater than this one, then for positive exponents, this graph is above this graph. But for negative exponents, this graph is below this graph. Alright, how can I prove it? The same story is repeating again and again. First of all, let's prove it for natural exponent. So a to the n greater than b to the n. Natural are obviously greater than 0. How to prove that? Well, if a is greater than b, then whenever we multiply n times a, obviously each component of this multiplication would be greater than each component of that multiplication, and that's why the result will be greater. Now, from this we expand it to positive rational numbers, because a to the power of p over q greater than b to the power of p over q, because this is equal to q's root of a to the power of p, and this is q's root of b to the power of p. If this is greater than this, then q's root should be also greater, and that's what this is. Alright, so we proved it for positive numbers. Now, how to prove, well, the opposite relationship to the negative numbers? Very easily, again, considering that for negative x, let me put a to the power of x for negative x, I will put it as minus absolute value of x. And this is b to the minus negative absolute value of x. That's what negative actually exponent means. So if x is equal to minus 2, its absolute value is 2. and that is minus 2. And then same thing here. Now, this is equal to a to the power of x. This is equal to, this is equal to 1 over a to the power of absolute value of x. This is equal to b over to the power of x. Now, absolute value of x is a positive, so this denominator is greater than this denominator because we have just proven it. But if we took inverse, we will have an inverse relation between them. So if this denominator greater, then the fraction would be smaller. So that's how we have proven this one. Now, so basically what we have done here, we have proven that in these two cases, when both of them are greater than 1, then the graph both are increasing to infinity in this case, and both decreasing to 0 for x less than 0, but one function would be above another to the right of 0 and would be below to the left of 0. Now, what if a and b are less than 1? Well, the situation is absolutely symmetrical. Let me just write it down, and I will just leave the proof to you. So if a is less than 1 and b is less than 1, let's say 1/2 and 1/3. Well, basically the story should be exactly the same, but opposite. So if this is the graph, this is, let's say, 1/2 to the power of x. Now, if you have 1/3, then it should be 1/3 to the power of x. Now, since my denominator is greater, then it goes down to 0 faster. 1/2 times 1/2 times 1/2 would be above 1/3 times 1/3 times 1/3. And on the left side, it would be exactly opposite. So we can actually do the following. So the function a to the power of x would be less than b to the power of x for x, yes, and a less than b. Okay, so if a less than b, then the value of a would be, of a to the power of x would be smaller for negative, and it would be bigger for positive. Let me check. The graph I know is correct. So if a less than b, so a is 1/3 and b is 1/2. So 1/3, no, yes. A is 1/3, b is 1/2. No, it looks like I just mixed it. 1/3, 1/2. 1/3 to the power of x is smaller for positive x. I'm sorry, for positive x. And this is for negative x. Right. It should be an opposite, right? Okay. So basically, this is exactly equivalent to the previous case, and the proof is based on the fact that if a is less than 1, then 1 over a is greater than 1, and 1 over b is greater than 1. And that's why we can use the previous theorem for 1 over a and 1 over b. So if a is less than 1, then 1 over a is greater than 1 over b, right? And therefore, 1 over a in the power of x would be greater than 1 over b to the power of x for positive x. And that's what actually gives an opposite equation for denominators of these two members. And same thing with this one. All right. Is that it? Yes. So again, if base is greater than 1, then the graph looks like this, and this. This would be 2 to the power of x, this will be 3 to the power of x. The greater the base, the higher it is for the positive x, and the lower it is with the negative. Now, if base is less than 1, then situation is kind of an opposite. So keep in mind these graphs. I think that all the properties which I was talking today are the foundation for these graphs. Now, I will explain in more details the story about graphs in the next lecture. So this one was just an illustration, graphical illustration of all these properties. But again, the purpose of the properties is actually to draw nice graphs. Monotonicity, greater than 1 or less than 1 based on the value of argument and the value of the base. So all these properties are very important, and they're all based on the most important property of all exponential function, which is this. Okay, that's it for today. Again, next lecture will be about graphs. I do suggest you to take a look at the notes to this lecture, which are accompanying the lecture on the unizor.com website. And I've also offer some exercises, problems, and exams. For those who are registered, you're welcome to take exams as many times as you want. And I would also like to encourage the parents to basically be supervisors for your students. And unizor.com actually allows you to register as a supervisor, and then you will be able to control the whole educational process of your students. That's it. Thank you very much. Hi, I'm Zor. Welcome to Unizor Education. I would like to talk about graphs of exponential functions. We did learn about what exactly exponent is, how to raise some number into some power. We did talk about properties of exponential functions, and now it's time to use these properties and these definitions to basically chart how the exponential functions look like on the graph. Now, before that, I would like actually to encourage you to go again through the lecture about the graphs in general, and I will remind certain properties of the graphs relative to these particular problems which I'm going to present right now, which are related to exponential functions. So very, very briefly, for details, I do refer you to the lecture about the graphs. So if you have a function, what happens with its graph if we will do certain transformations with argument or the function itself? Well, the easiest, for instance, is what happens with this graph if I add a to the function. Well, basically the whole graph moves up by a. Well, if a is negative, it's obviously down. And the form and the shape of the graph actually doesn't really change at all. Now, what happens if instead of adding to the function, I will add to the argument? Okay, in this case, the graph goes to the left by a, or if you wish, by minus a to the right. Why? Again, I refer you to the lecture about graphs. It's very easy to prove this. But in any case, in this case, if a is positive, the whole graph moves to the left. If a is negative, to the right by absolute value of a. Now, next transformation. What happens with the graph if I multiply an argument by a? Again, it's very easy to prove that if a is the positive number, let's say the a is greater than 1, then the graph is basically squeezed towards the vertical y-axis. If a is positive but less than 1, then it's basically is stretching. And the ratio is a. If a is greater than 1, it's squeezed by a. If a is less than 1, it stretches by 1 over a. If a is negative, it's basically two transformations. First, you do what is required to do for the negative thing. For instance, if a is equal to minus 1. Now, how this graph looks relative to this one? Well, it's basically a symmetry. You transform graph from this way to this way, and that's it. Because whatever was happening with a positive x now is happening with a negative x. So we covered this one. And finally, what if you multiply the function? Well, then again, this is a vertical transformation. Whatever you do with the function, it's always vertical. Whatever you do with argument, it's always horizontal. So in this case, it's stretching or squeezing by a, depending on whether a is positive or negative, and whether it's greater than 1 or less than 1. If it's greater than 1, it's just stretching. If it's positive but less than 1, it's squeezing by 1 over a. If it's negative, you first reverse the graph this way, and then do the stretching or squeezing. And finally, what if the situation is complex one, which is this? So you do some linear transformation on argument and linear transformation on the function. Well, this actually you have to do step by step. So let's transform the graph from this to this in steps. So first we do this. You know how to do this. Then you do this. We need plus c, so it's this. So first this is a horizontal stretching or squeezing. Then this is a horizontal shift by c over b. Then you multiply it by a. And then you add b to the result, which means you're stretching vertically, and then you're shifting vertically. So these are sequences, sequence of steps which you have to do to transform from this to this. So we'll do it step by step. And now let me just go straight to the problems related to graphs of different exponential functions. Now this was a short, refreshing course on how the graphs are transformed. And let me repeat again, go to the graphs lecture to get into the details why it's happening the way how I have described. Now, let's go to these 6 different graphs, and I will use the properties which were described in the previous lecture. So, the function y is equal to 2 to the power of x plus 1. X, y, 0. Now, all exponential functions, and in this particular case it's 2 to the power of x, are going through the point 0, 1. because if x is equal to 0, 2 to the power of x is equal to 1. Then 2 to the power of x is rising to infinity as x goes to plus infinity, and goes to asymptotically to 0 when x goes to negative infinity. So this is function 2 to the power of x. Now, how can I transform it to plus 1? Well, very easily. It used to be the x-axis as an asymptotic boundary for this particular graph. So now, since we are shifting everything up by 1, this would be the next asymptote. And the whole graph will be, instead of going through 0, 1, it will go to 0, 2. So the graph will be like this. The whole graph is shifted up. So this is y is equal to 2 to the power of x plus 1. So we did only one transformation. We started with 2 to the power of x, which is obvious how it looks, and then just shifted it by 1 upwards. That's it. Next. Y is equal to 1/2 to the x plus 1 minus 2. Okay, so let's do it one by one. First, we do 1/2 to the power of x. That happens in this particular case. Now, this is the case when the base is less than 1, which means that the function, instead of going this way, it goes this way. So this would be the graph, and this is the point 1. Okay, so this is y is equal to 1/2 to the power of x. All right. Next, what we have to do is, we have to do, instead of to the power of x, we have to raise it to the power of x plus 1. So we add 1 to the argument of this function. Now, if we add 1, the graph shifts left by this way. So instead of intersecting the y-axis at point 1, so instead of going through point 0, 1, it will go through point minus 1, 1. However, the asymptotic behavior as x is increasing remains the same. So this will be basically the same thing. By the way, just as a verification, in case x is equal to 0, the function is equal to 1/2 to the power of 1, which is 1/2. And this is the function y is equal to 1/2 to the power of x plus 1. So we have shifted the graph to the left by 1 unit. So whatever was 0, 1 becomes minus 1, 1. Now, the last thing is we have to subtract 2 from the function, which means the function moves down by 2 units. Well, this is 1 unit, so this would be minus 1, and this would be minus 2. So this point will go to this point. The x-axis as an asymptotic line would actually be axis shifted down. So this would be our asymptotic line. Now, the function used to intersect the y-axis at point 1/2. So we shifted down by 2, so it would be here, which is minus 1.5, right? And probably it would be interesting to know when this function actually intersects the x-axis, because the behavior would be like this, right? So this is one interesting point. We have already calculated it. When x is equal to 0, it's 1/2 minus 2, which is minus 1.5. Now, when does the function equals to 0? That's interesting. When exactly it crosses the x-axis, when y is equal to 0. Well, if y is equal to 0, let's just consider 1/2 to the x plus 1 should be minus 2 equal to 0. So 1/2 x plus 1 equals to 2. So when minus 1 to some degree is equal to 2, when the degree is equal to minus 1, right? 1/2 to the minus 1 is equal to 2. Now, when minus 1 is x plus 1, when x is equal to minus 2, right? So this is actually a point minus 2. This basically ends the reconstruction of this graph. So it goes through the point minus 1, minus 1. That's what used to be this. Crosses the y-axis at minus 1.5 and crosses x-axis at minus 2. That's it. Next. Okay, y is equal to 3.5 to the power of 2x plus 1 plus 2. Well, this is as complex as it can be, really. I mean, the linear manipulation with an argument and some linear manipulation with the function itself. All right, so let's do it step by step. First, we start with 3.5 to the power of x. This is something which we start with, right? So what's the graph of this function? Well, the base is greater than 1, which means it's increasing. So if this is point, it goes this way. So this is 3.5 to the power of x. That's easy. Next we do 3.5 to the power of 2x. Now, what does it mean that I'm multiplying argument by 2? It means that the graph actually should be squeezed towards y-axis because if I squeeze it by the factor of 2, then multiplying my argument by 2, I will return it back to the place where it was, and that's how my value of the function would be exactly the same. So the function, the graph would be squeezed. Now, just as a reference point, if my argument is equal to 1, my original function is equal to, well, that's obviously not to the scale. Let me just do it slightly differently so it will be a little bit better as far as the scaling. Okay. Now let's consider that 1 is here, 1 is here. Now this is 2, this is 3, this is 4. So 3.5 would be here. So the function actually goes this way. So as x is equal to 1, my function is equal to 3.5 to the power of 1, which is 3.5 here. But now, as I'm squeezing it towards this particular, towards the y-axis, now it will be in the 1/2. The same value, 3.5. So it will be this way. this also would be. So on the left, for the negative x, the new graph would be below the old one. On the right, when the x is positive, the new graph would be steeper and closer to the y-axis. Okay, so that's 3.5 to the power of 2x. Now I have this. Well, I can do it in two different ways. I can always represent 3.5 to the power of 2x plus 1 as 3.5 to the power of 2x times 3.5 to the power of 1, because the powers are exponents are added together, right? So I can actually multiply the function by 3.5. Or, alternatively, I can do it differently. I can do it this way. That's also 2x plus 1, right? Now, both approaches, one means I'm multiplying the function by 3.5, which means everything goes to the right of the 0, it will be steeper by 3.5 times, and on the left it would be closer to the 0 because it's less than 1 by 3.5 factor. So that's my multiplication by 3.5. But adding to the argument means that I have to really shift the whole graph to the left by 1/2. And interestingly enough, we are supposed to get exactly the same graph, right? So how now I don't want to prove that this is exactly the same. I'll just basically build both cases separately. So in one case, let me just do it on a different scale. I'm multiplying by the factor of 3.5, which means this point will go to somewhere here, this point will go here, so it will be something like this. Now, if I'm shifting by 1/2, it means I'm shifting to the left by 1/2. And that also would be something similar to this, right? So basically the result should be exactly the same thing, and we shouldn't really worry about how we will approach it, because it's still the same. So in any case, if I will shift it, let's say, by 1/2 to the left, my new graph would be something like this. This is minus 1/2. It would be 1, but everything else would be something like this. Well, I'm not sure that it will probably be something like this rather. Again, I don't want to put too much artistic talent into this, but basically the graph of 3.5 to the power of 2x should be shifted by 1/2 to the left. Now, just as a reference point, you can check what exactly would be the point where the graph is intersecting the y-axis. That happens when x is equal to 0, and the value of this, if x is equal to 0, would be 2 times 1/2 is 1, so 3.5 to the first degree, so it'd still be 3.5. So the graph would intersect here. So again, my artistic talent is challenged here. Would be something like here. Now, on the different note, if I have this represented as this, if x is equal to 0, this is 1, and the result is also 3.5. And obviously that's how it's supposed to be. So in any case, when x is equal to 0, y would be equal to 3.5. And the graph would look like this. And finally, plus 2. What does that mean? It means that this asymptotic line should really be shifted to this position, up by 2. And the whole graph, obviously, it used to cross the y axis at 3.5, now it would be 5.5 somewhere here, so the graph would look something like this. What's most important in all these manipulations is to realize how to do step-by-step transformation of the original graph, which is 3.5 to the power of x, into whatever the graph you have. So this is just an illustration of the steps necessary, and I will repeat it for a couple of other graphs as well, so I'm sure you will understand the point. Okay, next, 1/4 to the power of minus x minus 1. Well, we can do it differently, but let me do it straight. First, I will draw 1/4 to the power of x, which is this, and then I will do multiplication by minus 1 in the argument. Now, multiplication by minus 1 means, as I was saying before, reflection relative to the y-axis. So actually the graph would look now like this. And minus 1, which means we go down by 1, so the asymptote will be here. So it will be something like this. So it will go to 0, 0, because as x is equal to 0, this is 1, 1 minus 1, 0, so it will go through this. So this is basically the way how the graph would look. And this is asymptote. Now, let's do it slightly differently. We know that negative exponent means 1 over the corresponding positive exponent, right? So 1 over x, 1/4 at the power of minus x is the same as 1 over 4 to the power of x, which is 4 to the power of x. So I reverse it, right? So it's basically 4x. And 4x really looks like this. 4 to the power of x. And 4 to the power of x really looks like this. So instead of doing this, we can always do this. Which basically means exactly the same thing. All these transformations are leading to exactly the same thing, because after we draw 4 to the power of x, we just have to subtract 1, which means exactly like this. That's it. And in the future, again, if you have something like negative exponent, you can do both things. You can transform the function first and then draw the graph. Or you can draw the graph and then reflect it symmetrically relative to the y-axis. Doesn't matter. Okay, 3 to the power of minus x plus 4. 3 to the power of minus x plus 4 minus 4. Okay. I will introduce even more transformations in this particular case, because I can actually, before starting thinking about how the graph actually looks like, I can always transform it in the following way. It's 3 to the power of minus x times 3 to the 4th minus 4 is equal to 3 to the 4th is 81 times, now 3 to the power of minus x, I can always put 3 to the power of minus 2 to the power of x minus 4. Because if I'm raising something into one power and then to another, that's the multiplication of exponents, right? Which means 81 times 3 to the power of minus 2 is 1 over 3 to the power of 2, which is 1/9 to the power of x minus 4. Now, why did I do all this? Well, because this seems to be a little easier than this, that's all. So I have to do two transformations. My original graph would be 1/9 over to the power of x, which is this. This is 1. Since 1/9 is a base less than 1, the graph would look this way, asymptotically approaching the x-axis as x is increasing to infinity. Now I have to multiply it by 81, which means instead of going through the point 0, 1, it will go through point 0, 81. So it would be something like this. But it will still be approaching 0, because even if you multiply by 81, small value remains still small and increasingly closer to the x-axis. And now I have to shift it by 4, which means my asymptotic line would be here, -4, and everything else is the same, basically. Now, for some kind of a exercise, you can always find out what exactly are these points of intersection. This is when the function is when the function has an argument 0, which means this is 0, so this is 1, so it's 81 minus 4, so it's 77, which means it goes this way, higher than that. It's positive. From 81 down to 77. Now, the point where it crosses the x-axis is when it's equal to 0, right? So if I will equate it to 0, 3 to the power minus x plus 4 minus 4 is equal to 0. So 3 to the minus 2x plus 4 is equal to 4. And it's kind of difficult to calculate, but, well, what if this is 3, for instance? If it's 3, then this is supposed to be 1, so x should be equal to 3 seconds. If it's equal to, let's say, 9, it would be 2, so x should be equal to 1. So for 4, it would be somewhere between 3 seconds, 1.5 and 1. So wherever this point is, it should be something like 1.4 or something like this. Anyway, this is the behavior of the graph. Don't pay attention that this is just 1.5 or something like this, and this is 77. This is a scaling issue, and obviously I'm not drawing to the scale in this particular case. What's important is that I have made this particular transformation or simplification, if you wish, before charting this particular graph. At the same time, I could have done it in a little bit more classical way, if you wish, which means I would do this. 3 minus 2x minus 2 minus 4. So I would start with 3 to the power of x, and this is this. Then I would multiply it by -2, which means I would reverse it, I would symmetrically reflect it relative to the y-axis, which is this, and then stretch it vertically by 2, so it would be something like this. Then I would subtract 2 from the x, which means the whole graph should be shifted to the right by 2. So it would be something like this. And then down by 4, so it would be like this. More or less the same shape. And again, you can calculate all the points of intersection with axis. But that's the same graph, just differently obtained through different transformation steps. Okay, And the last problem. These are all exercises of basically the same thing. Minus 2x minus 2 minus 2. Okay. Let's do it in a more, I would say, classical approach. So first we do 1/2 to the power of x, which is this. This is 1, this is 0. Then, so this is 1/2 to the power of x. Next is 1/2 to the power of minus 2x. So it's reflecting relative to the y-axis because it's minus, which is this, and then stretching it by the factor of 2, which means this. Next is 1/2 to the power of minus 2 x plus 1, right? To get minus 2 here, I have to, which means the whole graph shifts to the left by 1 unit. So it would be something like this. And finally minus 2, which means the whole graph goes down by 2 units. So it would be minus 2 would be something like this. And at point 0 it's equal to 0 minus 2, so it's reverse, it's 4 minus 2, 2, so it would be something like this. So it should be something like this, it should be 4. And where it crosses the x-axis, that's when the y is equal to 0, let's calculate what it is. If this is equal to 0, it means 2 is equal to 1/2 to the power of minus 2x plus 1, or 2 is equal to 2 to the power x plus 1. This is 1, so x is equal to 0. So it's interesting. No, it can't be 0. It cannot be 0. No, it minus, right. X plus 1. Sorry. Yes. So which means 2x plus 1 is equal to 1. So x plus 1 is equal to 1/2. X is equal to minus 1/2. So this point is minus 1/2. So that's basically it. I was trying to show how from the first basic graph which you have, you can transform it into any other form which has some linear combination of arguments and the functions. It's not easy, it just takes some practice, and if you would like, you can just do it yourself many times. In any case, what's important to remember always is, for exponential graph, the basic most important point is, if base is greater than 1, it's increasing this way and goes down to 0 to the left. And if base is less than 1, that's the other way around. So it goes to 0 when x goes to plus infinity, and it goes to infinity when x goes to minus infinity. Everything else basically is a consequence from this. That's it for today. Thank you very much, and good luck.